Hey guys, today we're going to look at the extreme value theorem. Now, extreme value obviously implies extrema. Now, when we're looking at the extreme value theorem, we use it to find the coordinates of the absolute extrema. So we're going to go ahead and review first the difference between relative and absolute extrema. So relative extrema is basically when the function changes from increasing to decreasing or vice versa. So that is what we are most familiar with, and that's what we've been finding when we've been taking the derivative and finding those critical numbers. Your absolute extrema, however, are defined to be the absolute highest and lowest points on your graph. It doesn't necessarily mean that the graph has to change from increasing to decreasing or vice versa. So let's examine that. We have here the function f of x. And if I want to find the coordinates of the relative minimums, that's where your function changes from decreasing to increasing. So we have two. We have one here and one here. So those coordinates would be -3, 0, and 2, -6. For the relative maximum, it's just this one right here, which is at -1, 3. Now the coordinates of the absolute minimum, we have to look for the absolute lowest point of the graph, which is this one here, as we said before. So this is 2, -6. When we're looking for the absolute maximum, although this is a maximum, it is not absolute since the graph goes on forever up towards infinity. This particular function does not have an absolute maximum because infinity is not a real number, and extrema are considered as coordinates, not infinity. So infinity cannot be a coordinate because it's not a real number. So no absolute maximum. Now, if you notice here, on the domain of the given function, the absolute extrema occurred at the same place as the relative extrema, as you see here. So that can happen. Your relative and absolute can be the same coordinate. Let's look at another graph. Here we have the graph of a function on a restricted interval, meaning it does not go on forever and ever. If I were to find the coordinates of the relative minimum, that would be here at -3, -4. And then we have another here at 3, 2. Oops. The coordinates of the relative maximum is this one up here. So at -1, 4. For the absolute minimum occurs here at -3, -4. So the same coordinate as the relative minimum. However, the absolute maximum is this coordinate right there because that is the absolute highest point on the graph. Since this does not go on forever and ever, this would be considered the absolute maximum. So at 6, 5. Now your absolute minimums and maximums can change on the same graph depending on the interval that is defined. So for example, for this one, we are asked to find the absolute minimum and maximum over the interval -5 to -2. So that is, oops, well, whatever, you get the point. That is in this section here. So for the absolute minimum, that would be the same as before, so at -3, -4. But the absolute maximum is now at -5, 2. So we notice that that maximum did change because now the interval is different. For the next interval, we are given -2 to 3. So we're looking from this section to this section here. The absolute minimum would be this coordinate in that section, so at -2, 0. And the absolute maximum is now at -1, 4. For the last one, we are looking over the interval from -1 to 6. The absolute minimum of that section would be at 3, 2, and then the absolute maximum at 6, 5. So the one thing I want you to take away from this is that your absolute extrema can change on the same function if the interval changes. Now let's examine the extreme value theorem. Now, every theorem has like conditions, like something that needs to be true in order for you to apply that theorem. For the extreme value theorem, also known as EVT, the one condition is that f of x has to be continuous on the closed interval a to b. If it is continuous, then there is at least one absolute maximum and one absolute minimum on that interval. Keep in mind that absolute extrema, as we saw in the previous examples, can occur at the same places as the relative extrema or at the endpoints of the specified interval. So first we're going to determine is EVT even applicable for these particular functions? And we are given this interval here that is defined. Most of the time for questions like this, especially if it is an FRQ, you are not always told if the function is continuous or not. So you have to be able to determine if the function is continuous. So we have to keep in mind those rules of continuity for each of these functions. For this first one, f of x, we have 3x plus 2 over x plus 3. This is a rational function. And with rational functions, the denominator can never equal to 0, because if it is, then that means we have a vertical asymptote at wherever the denominator is equal to 0. So anytime you have a rational function, we're going to set that denominator equal to 0 and find the location of that vertical asymptote. Here we have a vertical asymptote at x is equal to -3. That means that it is not continuous at x is equal to -3 because there's a break. But -3 is in this specified interval. Therefore, EVT would not be applicable. So we would write EVT is not applicable because f of x is not continuous at x is equal to -3, which lies on the interval -5 is less than or equal to x is less than 0. Next, we have g of x is equal to 2x square root of x minus 3. This is a radical function. And if you remember, anytime you have a square root, you can never have a negative inside of a square root, because if you do, that means that we would have the imaginary unit. So when you're trying to figure out where this function is continuous, this, whatever is inside of the radical, has to be a positive number, or at least 0. So in order to figure out when it is continuous, we set the inside of the radical greater than or equal to 0. Because I can't have 0 inside the radical or any other number greater than 0. So when we solve, we get that x is greater than or equal to 3. So this particular function here is only defined for when x is greater than or equal to 3. Anything below 3 would be undefined, so not continuous. And x and that x is equal to 3 is in this interval. So this particular function, we would not be able to apply EVT again. So EVT is not applicable because g of x is only defined on the interval x is greater than or equal to 3. Which you can specify additionally, which lies outside the interval of -5 is less than or equal to x is less than or equal to 0. You can also have like an alternate way of writing this. I mean, it's really what comes more naturally to you, but you can say that EVT is not applicable because g of x is not continuous when x is less than or equal to 3, which occurs on the interval -5 to 0. So that's another way of writing the same information. Now for h of x, we have ln of x plus 7. Now just so you know, the ln of x, I want to show you the graph. this is the graph of the ln of x. Now, if you look closer, we see that to the left of 0 that there's nothing there. And additionally, if you just keep zooming in, you can see that the ln of x never touches the line where x is equal to 0. So it never touches the y-axis, meaning that there is a vertical asymptote here at x is equal to 0. So if you ever have the function ln of x, whatever is inside of ln has to be greater than or equal to 0 in order for the function, greater than 0, in order for the function to be continuous. So we would set x plus 7 to be greater than 0, because ln of x is not defined at 0, so we can't say greater than or equal to 0, and we solve. So x is greater than -7. So this particular function is continuous as long as x is greater than -7, which works for us because the interval that we're looking at is from -5 to 0. So for this particular question, EVT is applicable because h of x is defined and continuous on the interval x is greater than -7, which makes it continuous on the interval -5 is less than or equal to x is less than or equal to 0. So whenever you're determining if EVT is applicable, make sure that you state why and also restate the interval that's given. Now let's look at how we actually apply the EVT. So here we have the function f of x is equal to -x to the third minus 6x squared minus 9x plus 2. First, we determine whether this function is continuous, which obviously we can see that it is, but additionally, this is a polynomial function, and polynomial functions are continuous everywhere. So you can always just make a note of that on your FRQ, that polynomial functions such as f of x is continuous, since that is the condition to be able to apply EVT. Now, in order to actually use it, first we will have to find the critical numbers of the function. We don't necessarily have to verify that they are extrema. I mean, it's helpful to know, but we don't need to. Then we're going to test each critical number and the endpoints, since remember, absolute extrema can also occur at the endpoints, by plugging it into the original function and then to check which is the highest and which is the lowest value. So f prime of x is equal to -3x squared minus 12x minus 9. We can factor out the -3, leaving me with x squared plus 4x plus 3, and then we can further factor that to be -3, x plus 3, x plus 1. Make it equal to 0 to find our critical numbers, and we get that x is equal to -3 and -1. So now we're going to find those coordinates. So we take our critical numbers and we plug it back into the function. And not only are we using this, but we're also using the endpoints. So we're going to also test f of -4. And -1 is one of my critical numbers anyway, so we don't need to rewrite that. So now just to save on time, right, because since we have the graph, f of -3 is 2. F of -1 is 6, and f of -4 is also 6. I just look at my numbers. Since this is the lowest value, that means that I have an absolute minimum at -3, 2. And since both of these are my largest values, these are both my absolute maximums, which is at -1, 6 and at -4, 6. Now, what would happen if we change the interval to -4, 1? we would still have the same critical numbers, so we would still have to write out f of negative 3 and f of negative 1, but then we would also have to check for f of negative 4 and f of 1, my endpoints. So we're going to get those values. Negative 3, like we said, is 2, negative 1 is 6, negative 4 is 6, and f of 1 is negative 14. So this is our new absolute minimum, which is at 1, negative 14. But these two are still the absolute maximum since they are both still the highest points on the graph. Now let's examine when we don't have a graph. We have here f of x is equal to x plus 3 raised to the 2/3 on the interval negative 1 to 3. So first we have to establish if the function is even continuous. If it's raised to the 2/3, that means that this is equivalent to f of x is equal to the cube root of x plus 3 squared, since the denominator is the root and the numerator is the power. Now, if you have a cube root, you can plug in any number, whether it's negative or positive. It's only when you have an even root that you are not allowed to have negatives inside of the radical. Therefore, f of x is continuous on the interval negative 1 to 3. So now we're ready to actually work through the calculations. First, we got to take the derivative. So f prime of x is equal to 2/3 x plus 3 raised to the negative 1/3, since we have to apply the chain rule, and the derivative of the inside is just 1. So this is equal to 2 over 3 times the cube root of x plus 3. And we write it this way so we can find our critical numbers. Remember that the critical number can also occur when the denominator is equal to 0. So my critical number here is when x plus 3 is equal to 0. So x is equal to negative 3. But negative 3, if you notice, is outside of this interval. So this critical number is not going to apply for the EVT since it lies outside, and we're only trying to find the absolute extrema on that interval. So when it comes to testing our numbers, we're only going to test the endpoints. So we're going to look for f of negative 1 and f of negative 3. Positive 3. When we plug in negative 1, that is the cube root of negative 1 plus 3, so 2 squared, which is equal to the cube root of 4. When we plug in 3, that's the cube root of 3 plus 3, so 6 squared, which is equal to the cube root of 36. So my absolute minimum would be at negative 1 cube root of 4, and my absolute maximum would be at 3 cube root of 36. Now let's look at this question. We have g of x is equal to the ln of x squared minus 4 on the interval negative 3 to 6. So first we have to establish, is this even continuous? Keeping in mind that this is an ln function. So we take x squared minus 4, and it has to be greater than 0. Solving for x, we would add the 4, so x squared is greater than 4. And then square root both sides, we get that x is greater than 2 and x is less than negative 2. So when you're square rooting with an inequality, you know the square root is always plus or minus. So the square root of 4 gives you a positive and a negative 2. Just like when you are dividing a negative using inequalities, it switches the signs. Same thing with square roots. When you square root a number, you keep the inequality for the positive version of the number, and then you flip the inequality for the negative version of the number. Now, just to give you an idea of how this works for this particular function, I'm going to put these numbers on a number line. This particular function is only applicable as long as x is greater than 2 and x is less than -2. So we have this hole here where this function is not applicable, or it's not defined. So this function is not defined between -2 and 2, which is on the interval. So for this particular function, we would say that EVT is not applicable because g of x is not continuous on the interval, and I would use this right here, -2 to 2, which lies on the interval -3 to 6. Now I forgot to mention, if we have to justify our answer for, let's say, A, we would say EVT guarantees an absolute minimum of -1 cube root of 4 and an absolute maximum of 3 cube root of 36 because f of x is continuous on the interval -1 to 3. Now let's look at some sample multiple choice questions. In this first one, it says, which of the following functions of x is guaranteed by the extreme value theorem to have an absolute maximum on the interval 0 to 2 pi? So in order to determine if EVT is applicable, we just have to make sure that these functions here, or which of these functions here, is continuous on this particular interval. If you look at all of these functions, these are all rational functions. So that means that if the denominator is equal to 0, we would have a vertical asymptote that would make the function not continuous. So that's what we're going to do. We're going to set each of these denominators equal to 0 and solve. So 1 plus sine x equals 0. Or if you prefer, you can make it not equal to 0 to make sure that it would be discontinuous at the x value that you found. So we would subtract the 1 and we get sine of x cannot equal to -1. The sine value that gives you, or rather the angle that gives you a sine value of -1 is when x is 3 pi over 2. Now 3 pi over 2 is on this interval, and this is where we have a vertical asymptote, so it's not A. Now if we look at B, we do the same thing. X squared plus pi cannot equal to 0. We solve for x, we get x squared cannot equal to -pi, and if we square root, we get that x cannot equal to I square root of pi. This is an imaginary number. Now if that happens, that means that the denominator will never equal to 0. So it would be continuous everywhere because there are no vertical asymptotes. So the answer would be B. But just so that you can see, in case you got this and you were like, I don't know what that means, you can check your other ones. For both of C and D, the denominators are the same. So x minus pi cannot equal to 0, and we solve for x. X cannot equal to pi because there we have a vertical asymptote, and pi is on the interval, so both C and D would not be applicable, leaving me with only B. Now for this second question, now this is part of what would be an FRQ, and we're trying to find the absolute maximum value. If you're asked for the maximum or minimum value, they're asking about the y value. So we're going to go through our process here. We have to determine, is this continuous? Now sine and cosine are continuous functions because on a graph, it's just a wave like that. So we would say g of x is continuous everywhere. And like that, I have already established that EVT is applicable. And in the previous examples, I've been using full statements, but we don't necessarily have to every time. It's all what comes more naturally to you. I have established that it's continuous. That means that EVT is applicable, so I can just write that down. And this is enough of a justification for this particular question. Now let's go ahead and find that maximum value. So first we need g prime of x, which would equal to 2 sine x, since this is the same thing as saying sine x squared. So we would have to apply the chain rule. So we move the exponent, so 2 sine x raised to the first power times the derivative of sine, which is cosine. And the derivative of cosine is negative sine. You make it equal to 0. And now we're going to solve. So both of these terms here have a sign in common. So we can factor out the sine x, and we're left with 2 cosine x minus 1. We set each factor equal to 0. Sine of x is equal to 0 when x is equal to pi and 2 pi. For this one, we would have to add the 1, so 2 cosine x is equal to 1, and then divide the 2, so cosine x is equal to 1/2. Now cosine is positive in quadrant 4. Now keep in mind our interval here, we're only looking for from pi over 2 to 2 pi, so in this section here. So it's only one angle, and the angle that gives you a cosine of 1/2 in quadrant 4 is 5 pi over 3. So those are my critical numbers, and now I'm going to test each one. So we're going to test g of pi, g of 2 pi, g of 5 pi over 3, and the endpoint that we're missing, which is g of pi over 2. We're not going to do 2 pi because I already have it here. So we plug in all of these values into g of x here. So sine of pi is 0. 0 squared is 0, plus cosine of pi is negative 1. When we plug in 2 pi, sine of 2 pi is 0, so 0 squared is 0, plus the cosine of 2 pi, which is 1. Now sine of 5 pi over 3 is the negative square root of 3 over 2, which we're going to square, plus the cosine of 5 pi over 3, which is 1/2. When we square this number, that gives us a positive 9 over 4 plus 1/2, 3 over 4, plus 1/2, which is 2 over 4, giving me an answer of 5 over 4. For pi over 2, the sine of pi over 2 is 1. 1 squared is 1. Plus the cosine of pi over 2, which is 0, so 1. So if it's asking for my maximum value, the maximum value is 5 over 4. And that's the extreme value theorem.